Hello, everybody. In the last video, we left off with our horizontal branch star. Post-helium flash, the star ended up on the horizontal branch with a helium burning core surrounded by a hydrogen burning shell, surrounded by the envelope of the star. And now we are going to go into the final stage where we could say that the star is actually alive, the final living stage where we have fusion really occurring in the star. This final stage is called the asymptotic giant branch, and it's sort of like our red giant branch part 2. And this is where we can really see the rhyme and the reason, the logic of just following up, of building up an ash core and seeing how the star responds. That's how we understood the ascension up the red giant branch, and that's exactly how we're going to understand ascending the asymptotic giant branch. So where are we on our HR diagram of stellar evolution, looking at the evolutionary tracks? We have gone from 1 to 2 our subgiant branch, 2 to 3 ascending the red giant branch. And then the helium flash happened at 3, which moved us down to 4 on the horizontal branch. And now we are going to ascend the asymptotic giant branch, going from 4 to 5, which is very, very, very similar to when we ascended the red giant branch. So we're going to see a lot of commonality. There's just going to be a slightly different structure to the core. All right, so here we are at the beginning of the asymptotic giant branch. The star has been living its happy hydrostatic equilibrium life on the horizontal branch with helium to carbon and oxygen fusion in the central part of the core, surrounded by a shell of hydrogen to helium fusion. However, over time, as the central part of that core fuses more and more carbon and oxygen from helium, it's going to build up a higher and higher relative percentage of carbon and oxygen, eventually forming a central part of the core that's going to be made of carbon and oxygen completely, 100% carbon and oxygen, and the temperatures are not going to be sufficient to fuse carbon and oxygen into heavier elements. We will have a new ash core. So this is the second time that we've been talking about a fusion ash core. The first time is we developed a helium ash core, which caused us to ascend the red giant branch. Now we are developing a carbon and oxygen ash core, which is going to cause us to ascend the asymptotic giant branch. So roughly the same physics is going on in the core of the star. And we will see that we're going to have the same general trend, the same movement on the HR diagram of up to higher luminosity and to the right. So higher luminosity, higher radius, and a cooler surface temperature. So with our carbon oxygen ash core, that means that there's no fusion happening in it. The temperatures aren't high enough for carbon and oxygen to fuse into any heavier element, which means that gravity is again going to start to win in that part of the core, and it's going to start contracting under gravity. And as it contracts, that part is going to heat up, and it's going to heat up the entire core of our now asymptotic giant branch star. As the entire core heats up, that means that the helium burning shell immediately around that is going to start fusing faster. They're going to have increased fusion reaction rates of helium to carbon and oxygen. So our helium burning shell will have increased fusion reaction rates. And then surrounding that, we'll have our hydrogen burning shell, and the reaction rates will go up there as well. So yeah, we have a pretty complicated core structure. We have the carbon and oxygen ash core surrounded by a helium burning shell, surrounded by a hydrogen burning shell. And as the ash core contracts, all of the fusion reaction rates are going to go up because the temperature is going up, which is going to set off a lot of thermal pressure into the envelope of the star, which is going to cause the envelope of the star to balloon out once again. So as the star's envelope expands outward in response to the changes in the core, then it's going to become much, much larger, have a larger surface area to emit the increased amount of energy it's producing in the core. So its luminosity is going to go way up, which moves it up on the HR diagram. But as the outer part of the star, the surface expands away, it can cool down. The surface of the star will become cooler, which will move it to the right to colder temperatures on the HR diagram. The star will appear to be redder. So we're going to see movement up and to the right on the HR diagram. Let's go ahead and take a look at that graphically. While a stars on the horizontal branch is called a horizontal branch star. If we're talking about a sun-like star, it also gets the name of a yellow giant star. So here I have a giant star that's yellow, and let's see how it ascends the asymptotic giant branch. It becomes larger and it cools down, becoming now over a few hundred times bigger than the sun currently is, stretching out all the way to about the surface of Venus, maybe even to the surface of where the Earth is, depending on the specifics of the asymptotic giant branch star. And now we have a red giant, or on occasion, a red supergiant. And what do we have? And it's always good to keep tracking what the core is. And I cannot repeat this enough, just to help you actually keep track of what's going on in the core. We have a carbon and oxygen ash core. That's the central part. Surrounding that, we have a helium burning shell. And surrounding that, we have a hydrogen burning shell. And then we have the rest of the star, the non-fusing envelope. And this is where we have something absolutely critically different. Oh, and before I actually get into the critically different part, I want to go ahead and this is sort of a strange name, the asymptotic giant branch. So, where does the name asymptotic giant branch come from? You've probably already seen, and I've explained that it's very similar to the red giant branch. So, let's just imagine that I drew a line just extending the red giant branch. Just imagine there was no helium flash, and I had this nice smooth transition into uh, having a carbon ash core with a helium ash shell with no helium flash. So we didn't have this little chicane where it jumped down the horizontal branch. So imagine it just kept going. You could draw a line just going up on the HR diagram. Think of it as a mathematical function. And now if we look at the red giant or the asymptotic giant branch, we would notice that that line approaches the continuation of the red giant branch, getting forever closer, but never actually overlapping with it since it started at a slightly different starting point. We call such things in mathematics asymptotes. So we would say that the asymptotic red giant branch is asymptotically approaching the continuation of the red giant branch. So we call it the asymptotic giant branch. The name is derived from mathematics. Okay, now that I've gone a little bit of a side to explain the name, let's talk about why this is so significant and why this is going to be the last living stage for our sun-like star. For low mass stars, remember that's all stars that have mass less than 8 solar masses. There's simply not enough mass in the star that as that carbon oxygen core contracts under gravity, eventually becoming electron degenerate, and more helium is fused into carbon and oxygen piling onto that, and then more hydrogen is fused into helium piling onto the helium burning shell, just making the core more and more dense, and therefore it's going to keep trying to contract under gravity, and it's going to get hotter and hotter and hotter and hotter. How hot can it get is dictated by the total mass of the star. And if you're 8 solar masses or less, your core temperature can never reach the next fusion ignition temperature. You can fuse carbon and oxygen into heavier elements, but to kick off the next stage of fusion, the next level of fusion, the next one would be carbon fusion into heavier elements, and that has a ignition temperature of 600 million Kelvin. In stars less than 8 solar masses, will never have core temperatures that high. They simply don't have the mass to drive the core temperatures to that temperature, which means there will never be another round of fusion. We can't play this game of starting a new round of fusion, turning the ash core into a new fusion core. That game is done, which means that the tank is running out of gas. It's running out of things in the star. It can fuse into heavier elements. It's running out of a way to power itself as a star. And if you're curious, I don't require you to memorize the equations past the triple alpha process, but there are several different pathways of carbon fusion. You can do carbon fusion into neon. You can do carbon fusion into sodium. So you can see that you're just building up heavier and heavier elements. This sodium, however, will decay quickly to neon. All right, so now we have this carbon ash core that's electron degenerate, and it'll never reach the critical temperature, the fusion ignition temperature, to fuse that carbon and oxygen into heavier elements. But we do have this situation where it's electron degenerate, or where we have an electron degenerate part. So we have an electron degenerate core. What does our star look like now? What does our asymptotic giant branch star look like? The radius for a sun-like star, so our sun at this stage will be about 300 times larger than it currently is, which puts its surface right around where Earth is or so. And now, just depending on the specifics, it'll be a luminosity class 1 or 2. So we've sort of gone through all the luminosity classes. As we can see, the luminosity classes are really just looking at the death throes of a star. And this is where we are for our asymptotic giant branch star. Now I want to go ahead and give you a nice big clean picture of this so I can show you and explain what is about to happen that is really kind of amazing with this star. How this star is actually going to go through its death throes as it runs out of things to fuse, as it runs out of gas. So over here, I have a nice graphic of what our asymptotic giant branch star looks like. This is a cross section. Here is our carbon and oxygen ash core, surrounded by a helium burning shell, surrounded by a hydrogen burning shell. And then all of that is in the envelope of the star. So the colors are the core of the star, and here I have the envelope of the star. The temperatures are still starting to go up, and the core is getting more and more electron degenerate. You are actually going to end up with a little bit more oxygen being produced in this stage, because on the boundary between this carbon ash core and this helium burning shell, you have some pretty high temperatures, which makes fusion reactions a little bit easier to proceed. So you'll get on that boundary a good bit of carbon fusing with helium to produce more oxygen. We also have this weird situation where, excuse me, where with this electron degenerate core, our helium burning shell right on that boundary with the degenerate core is going to go through a series of helium flashes, helium shell flashes, not in the core. Very, very similar, where you're basically building up electron degenerate matter. Then it's going to hit the critical temperature to fuse that helium into carbon. And then it's going to proceed just like we talked about the helium flash, where it's going to proceed in a thermonuclear runaway very, very, very quickly and dump a whole bunch of energy into the envelope of the star. So it's going to dump that energy every time one of these helium shell flashes happens. It's going to dump the energy into the envelope of the star, causing it to puff up. And as it puffs up, the surface will become cooler. But eventually, as it puffs up, everything's going to expand out. And then as things expand out and as these helium flashes expand out the core of the star, it allows it to cool, so it'll start to contract, and then the star will start to contract again. Just like we saw that post-helium flash, we ended up with a smaller star overall. And this is going to happen over and over and over and over again, where you can build up the conditions for one of these helium shell flashes, and then it'll flash, cause an expansion and a contraction, build up the conditions for another helium shell flash, another round of expansion and contraction. So this is going to be a repeating cycle of expansion and contraction over and over and over and over again. So before I actually go through and show you all the like how this is going to proceed, what is going to go on with these pulsations as these helium flashes in the core, as the star is running out of gas and fusing all the available material into carbon and oxygen, which will never be able to fuse. The extra little detail that I'm going to sweep under the rug because I don't want you to memorize it, because it starts getting a little bit too nuanced and too much hard to keep track of, that technically, as you move away from the helium burning shell, there is a shell where you have helium ash. So you have a helium ash shell between the helium burning shell and the hydrogen burning shell. A detail that you don't have to remember, but it is part of the core of the star. And I felt really, really bad about not giving you the full view of what it is. Extra detail, don't worry about it. Most textbooks gloss over this fact. I just wanted to go ahead and be completely truthful and show you the entire situation. Okay, so now let's go back to this series of helium flashes that are causing an expansion and a contraction of the star over and over and over again. So we'll have one of the helium flashes, which will set off an expansion, and then it'll overexpand and it'll contract. Set up a helium flash, expand, contract, expand, contract over and over and over and over and over again, each one of these cycles of expansion becoming a little bit stronger than the previous one. So you'll see these oscillations, and the y-axis here is radius, how big the star is, and this is time. So you're looking at over time, an asymptotic giant branch star is going to go through these pulsations. It's going to get larger, smaller, larger, smaller, larger, smaller, larger, smaller. And each one of these is kicked off by one of those helium shell flashes. And each subsequent oscillation grows in strength. And eventually, we'll watch we'll watch this one more time. As you can see that each time it's getting a little bit stronger and is expanding out a little bit larger. That surface is getting further and further and further and further away from most of the mass of the star. And eventually, some of that envelope material, the outer part of the envelope material, will get kicked so it's moving faster than the escape speed of the star, the escape velocity of the star. And so eventually those outer layers, as we increase in the oscillations and they really puff out too far away, they're moving too fast to ever get gravitationally pulled back to the star. So they get ejected from the star. They become decoupled from the star and start going out back into the interstellar medium. And they do this at incredibly high speeds of about 10 of kilometers per second. So 10 kilometers per second, 20 kilometers per second, 30 kilometers per second. These are very, very, very high velocity ejection of basically shells of the non-fusing envelope that are now going back out into the interstellar medium. And with these high velocities, these are technically creating shock waves. And these are the types of shock waves that we were talking about that can set off a new round of star formation. So the death of a sun-like star can be the birth of a new round of stars. This nice little cycle going on. And as it goes through these repeated cycles becoming larger, that means that the outer envelope is expanding and cooling, so it's going to get cooler and redder. Then it's contracting and get hotter and bluer. Overall, the luminosity remains roughly the same. It fluctuates a little bit as those two things of hotter and larger, or hotter and smaller, and cooler and larger balance each other out. But the point I want you to walk away with is that we have this series of expansions and contractions, and then we're going to start shedding outer layers of the star. The star will literally start ejecting all of the non-fusing envelope, and it'll continue to do so until it ejects pretty much all of the non-fusing envelope, everything that can't be fused, leaving behind only the now almost completely carbon and oxygen fusion ash as a very, very dense core. And we can actually see this. We observe this. So this is a star called R Sculptoris. It is an asymptotic giant branch star. It is very sun-like, about 1 to 2 solar masses. It's probably a little bit more massive on the main sequence. But here we're going to look at this in 2 different wavelengths of light. Here's the visible light image, and the star is actually here in the central region. And what you're seeing here, you can almost pick out these dense shells of material going away from the central part of the star. We are seeing the ejection of the shells. And all this material is cooling down. And you get all sorts of really cool chemistry going on in there. This is where you form a lot of the universe's silicates, things like that. But you can see that you have these shells of expelled material. What's even more amazing is if you look with high resolution radio or microwave images like the ALMA interferometer can look at, here you can see the star in the center. And here you can see all of these shells where each expansion kicked off a little bit more of the outer envelope and it contracted, and then kicked off a little bit more, kicked off a little bit more. And we can actually measure and see that each one of these pulses, these expelling of a new shell material, are separated about 10,000 to 50,000 years. And the pulse itself, based on how wide the pulse is, happens really, really quickly, only a few hundred years long. It also has kind of this cool spiral structure. And here's the outermost shell. And this used to be the envelope of the star. So we are throwing away all the fusible material, all the envelope of the star is getting expelled back into the interstellar medium, slowly exposing the core of the star. And the core of the star will never reach temperature sufficient for another round of fusion. So at that point, you're going to stop fusion and you'll no longer be a star. This is going to set the stage for one of the most beautiful, opinion, not a fact, although it's pretty close to a fact, astronomical objects out there, the last death throes of a sun-like star, a planetary nebula. That's going to be the subject of our next video, and I will see you there.